In this video we're going to look at a couple of different kind of digital inputs. We're going to look at these two on page 258 of the textbook for the design engineering students. Those of you who aren't studying design engineering, just interested anyway, we're going to first of all look at a slotted optical switch. Now for the students it's a good idea to know how these work because they do come up in the exam. There is a past paper that deals with one of these. And it's basically looking at one of these things in like a tube train turnstile, so the ticket barrier, how it allows you in through the turnstiles. Now what happens here is we've got holes and we've got shutters, as it were, slots, and it's able to count with one of these optical sensors. So there's a light and a sensor either side, and they often look like this. Now I've just bought one of these cheap things from China, and it's one of these things here. They might be slightly different. Some have light dependent resistors. This one's got photo transistors in it. So in other words, it will generate a tiny weeny little bit of current just from sensing the light on the other side. So we've got E for emitter, which is basically an LED. Now it might be infrared, in which case you can't actually see a light. It doesn't look like we can see a light in this one here. And then we've got these two little photo transistors, which are basically the first one. You notice it hasn't got a base. Remember we were talking about the input of a transistor called the base. This one, basically the base is the light, so it'll just, as soon as light lands on it, it'll get a tiny weeny amount of current, and then it'll feed this one, which amplifies it. Now this is very much effectively something called a Darlington pair, and that's a pair of transistors which basically amplifying each other. So if you start off with a tiny weeny voltage current, hardly anything that you can use, you piggyback them like this, and they will able to amplify it so that it's something useful. Now here I've got a little laser cut jobby which I made this morning. It's just basically one of these slotted discs, and I've mounted this thing, as you can see, just in between here. Now I can't quite see from here, but just so you know, when looking at this schematic here, we've got D for detector, E for emitter. The emitter is just going straight off this rail here, which, like the other times, is just plugged into the output voltage. So I've just got a plus volts here off one of these common rails going onto this plus volts rail, and that's also powering the LCD as well as the emitter and the detector as well. Sorry, the detector is plugged into one there, but basically the detector is just sensing an analog. It's going into this input AD0, and we're reading an analog input there. So rather than on or off, it might work as on or off, but just in case we don't get the full range of off or on, we can just detect an analog range here. So what do I mean by that? Well, if we go into Circuit Wizard with this all plugged in, and I've just got a dummy program here, I can go to debug live like this, and I can read, once I press start, I can read the analog sensors. So looking here, we've got this value on A0 at 32. Now if I just very carefully move it, I can get it down as low as 16, 17. That's presumably when it's blocked. So there's no light being shone through this hole. It's in a slot at that point, so it's not actually shining through, and so we're getting a very low reading on the analog amount. And then I'll just move it right up, and let's see, we can go up to 100, 103, something like that. Let's see what the highest we can get. So it just takes a tiny little amount. Yeah, 104 I'd say. So we're going to, let's just stop debugging that. Okay, now what we're going to do here is just write a little program. So we're talking about 17 to 104, the range. So what I'm going to do is get an analog reading like this, and let's say is it in the range of 0 to low end? So let's say 0 to 40. Okay, you might want to tweak these readings just so that you can get a more accurate answer. And we're going to look at A0 like that. Okay, so is it dark? Let's copy that and then click on there, make another one. Now we're going to say, is it light? So rather than going 40, we'll give it a little bit of leeway. So if it's in that middle ground where it could be dark or light, it will just carry on checking until something's better. But we'll say something close. Again, like I say, you might want to tweak this. Now, if it's dark, yeah, okay, we'll go on. If it's definitely dark, we're now going to see, is it light? Okay, so what's happened there? If it's dark and then it's not light, it hasn't moved really. So let's have a little, hang on, that needs to swap yes and no like that. So is it dark? No, it's light. Okay. Is it still dark? No, it's light. Okay, there's a hole shining through it. Then as soon as you move it and it goes dark, yes. Okay, now is it light again? Has it moved again? Okay, so what you're looking for is it having been dark and then light. And if you go through both of those states, then we're going to take a variable here. So let's find this one here, increment. Okay, and I'm going to start with something called variable A. And I'm going to add 1 to that amount. Now, once I've done that, I'm going to plot on the LCD what that variable is. So here, what I want to do is write square brackets, this one here, and then A, like that. And you can see the variable is currently 0. It doesn't say square brackets A on the preview, it says 0, which is what the variable currently is. Okay, and then I'm going to go back to the start and carry on checking. So each time it goes through a sequence of dark to light, i.e. it goes through a hole and then a blockage, it adds 1. Excuse me, it adds 1 to the value of, the variable A, and then it plots it on the LCD. So let's just try that. We'll just run live and see what happens. I've put a little green dash on there so we can see if we can count up to 60. There's 60 slots here. So let's see now. Now it's got something from the old program here. Let's just see if that goes. Yep. So it's now checked these two states. It's gone dark to light and then it's added 1. So it's now saying 1 there. Now let's see if that works right the way through. You can see each time it goes dark to light, it will go up and up and up, and that all seems to be working quite nicely. Let's just spin it right the way around and bring that green little dash back to where I started. And it's close to there. Yep, it's almost there, 60. Now that might have just been because I was not quite on the line here. We've got a little reset button on these Genie project boards, so we can just try it again. Now I might want to put something on the LCD command here just at the beginning. In fact, let's just do that to make life easier. So I'm going to copy that LCD thing and then just put it up here. And then I'll just put 0 instead of variable A. So run live now. Let's see what happens. All right, let's see if that works then. So we've got 0 there. 22. And there you go. So yeah, that works nicely. 60 pulses. Now let's say what do we want? Let's say we want that as a degrees instead. So I'm going to just modify this a little bit. Now it would be as easy as just timesing variable A by 6 to get degrees. Now the trouble is if I go and do that with expression, the maths, or even do scale. Scale's a nice simple one. So if I take variable A and scale by 6, let's just see what happens here. Some of you might be able to guess what's going to happen. So we'll go back to the start, we'll press run, and oh, that one there, run live. So just upload that. So it starts at 0, and it just, can you see it just goes all over the shop when getting hardly the right numbers here, and it's actually kind of jammed on 51 for some reason. Now what's happening there is, let's say the first thing, okay, the first count, the first check, it's added 1 to A. Okay, so A is 1. It tells us, in fact, I wanted to put this here anyway. But even so, it's wrong anyway. So yeah, it's called A1. It's plotting A is 1. And then we're scaling it by 6. So A is now 6. And then it does this check here. And then it adds 1 to 6 because it's already 6. So it's 7. And then it scales 7 by 6. So we've got 42. And then 43, and then times 43 times 6. So it doesn't work if we've got the same variable. Our variable A is the number of dashes or slots counted. Now basically what we want to do here is have another variable. So we'll just go back to the gallery and get expression. And we'll say B, this new variable, which is the degrees, is A. Okay. Now that means A can go up and B will still be independent of that. And then basically I'll just move that down so we've got enough space. And then we'll scale B. B by 6. Now I could demonstrate this and show it's wrong as well, but there is also an issue with this. And that is we can only count up to 256 with these chips. They're 8-bit chips, and that's how much they store in their memory. There's a number of different ways around it. We could have 3 different variables, so we can have hundreds, tens, and units, all as separate variables, and it'll be an if check. So we'll have a compare here. If variable A is above 10, then add 1 to variable B. So in other words, if let's say variable, let's call them B, C, and D. So hundreds, tens, and units. B is hundreds, C is tens, D is units. So if D goes over 10, then you add 1 onto C, and you can count up with many more digits that way. It's a bit of a kind of long-winded way of going about it. Another much simpler thing to do would be, rather than scale it by 6, we could scale it by 0.6. And then we can just put a 0, a fake 0 on the end of this, which is always going to be there. So now if we just upload this, did I just check? Yeah, no, sorry, this needs to be B, because that is still plotting the number of slots. So let's just run that one, see how this works. So before it uploads, let's try and get that thing into the corner. There we go. Okay, it's at 0. And let's see. Right, 10, 20, 30, 40, 50, 60, 70. Now the trouble is this might not actually be as accurate as well, because it's scaled down from, so it's 0.6. It might be a fraction of something, and it does actually round it up or down to the nearest whole integer, whole number. So that might be an issue, and you might find when we get round to full circle there, no, it's all right, it says 360. Now given that the accuracy of this is 6 degrees, it's not super accurate. This is an accuracy of 10 degrees. It's probably going to be a similar kind of ballpark anyway. Another problem with this is, let's just reset. It doesn't know which direction we're going. It's just counting light and dark. So if I go up like that, 50 degrees, and then back down again, it's counted up still. So it doesn't know it's going backwards. And in the next half of this video, we're going to look at a rotary encoder, which is more of a kind of user input rather than this feedback loop. So this is very good for error checking motors, DC motors and things, telling them where to stop where they've got to an exact amount of rotation. But the second thing we're going to look at has the ability to sense when it's going forwards and reverse. Now you could even have a more complicated one of these that uses the same principle as the rotary encoder, which we're going to look at in a minute. You'd have to have two slightly different discs that are slightly out of phase with each other, and in a minute we'll just have a look and see how that works. So those things that record movement in two directions are known as rotary encoders. The textbook calls them quadrature rotation sensors. Basically what it is, it looks like a potentiometer, but actually it's a digital counter that you can turn in either clockwise or anti-clockwise, and it's got a few notches on it, so it's not a smooth rotation, it clicks as it goes through, and each click will count up a data variable. Now, without plagiarizing too much, we've got a quote here. This shows a nice little illustration of what we're talking about here. Now the pins on it, we've got two inputs here, clock and DT, and then this third input here is a switch. It's just a push switch on a micro switch on the actual knob. But we're really interested in these two inputs here. As well, you power it with plus volts and you ground it with 0 volts as well. But what happens when you rotate the knob is you'll get a pulse as these little discs pass these outputs. You'll get a switch. Now they're slightly out of phase. You can see they're 90 degrees if there's a 360 degree phase on each click. A quarter of a click means one of the inputs comes on, and then the next quarter they're both on, and then the third quarter just that one's on, and then the fourth quarter that's one's on. Now what that means is you can actually tell which direction it's going just by the fact that they're out of phase. So if let's say we read at this point where they're both off, if I know this input A, let's call it input A, comes on first, I know it's going this way. However, if input B comes on first, it's going that way. And that's effectively how you count. Now, how do we do that in Circuit Wizard? There's plenty of tutorials on how to do it in Arduino, but it's pretty straightforward. So what we're looking for, first of all, is to check to see, let's say we're looking at input 0 as output A. Let's call it input 0. What I'm looking for is to see that it's off. Now I could be in this trough or I could be in this trough, but we want to check to see we're in a trough rather than on a peak there. So we're looking for input 0 off. Now I'm going to just go around in a circle if it is off. If it isn't off. So if that's swap yes and no. If it isn't off, if we're up here, we're going to just look until we've turned just a quarter of a cycle until we're in this, or sorry, half a cycle until we're in that trough. Then what am I going to do? Well, I'm going to basically ask if the other one has been turned on. So, sorry, before I do that, I'm going to ask if this same one is on. So I'm not even going to look at input 1 yet. I'm looking for the point at which it's called the rising edge. So it could either be here or it could be going that direction. But the point at which it goes on. So again, if it's not been turned on, if it's not moved yet, so swap yes and no, I'm still going to be asking if it's on yet. So if it's turned just a tiny little bit, it goes into this state. If it turns on, so we've got a rising edge, either of these two, and it's well and truly on, then I'm going to ask the next question, and that is basically, is 1 on? At that point it rises, it's then going to see if this is on. So if it's rising on this one and one's not going to be on there, so I know it's going that direction, I can say increment the value. Increment. Let's just draw it out visually and then you can understand it. So then I'm going to say increment A, and then if it's not on, I'm going to decrement A, so reduce the value by 1. Okay, so let's look at the scenario. But before we do that, we'll just get all the flowchart written out. So then we're going to have LCD somewhere over. Okay, and then I'm going to just plot the value of A. So that will be square brackets A, like that. Now remember also, might want to have the LCD at the beginning. So just so we know the program's working, if we can just say something, hello, or yo in this case. So rather than having a variable here, I'm just going to say yo. Okay, I've got a funny little squiggle there, but it doesn't matter. Now, what happens here, this will get displayed until, as long as we don't put it there, because if we put it into this one, it will only get displayed for an instant, and you won't even see it before it kind of resets it with yo. So we want to make sure this is at the beginning, and then as soon as you turn the dial, we'll get a change in the value. But basically, it'll only refresh the LCD when it's gone through a whole. So basically, let's look at the scenario. So we're looking for nothing's going to happen until this is in the off state. So it's either in this state or this state. And then we're looking for a rising edge. So let's say we're going this way, and we're looking for that point where it goes from off to on. At that point, if input B, D1 is off, let's say this is increment, so if D1 is off, well in this case it's decrement. If it's risen up on this edge, so it's been turned the other direction, D1 is going to be on at that point, so we'll know to increment in this case, get the right way around. But yeah, whichever way, you can trial and error it and then swap increment or decrement round. And that's pretty much it. That's how this thing works. So let's just see if that works. As you can see, I've got yo written there. So it's the first state where it says LCD is yo. Now, as soon as I turn the switch, if I go clockwise, it looks like it's counting down. So it's not very intuitive, that, but it does work. Now, there's two ways of fixing that. Either we can swap the increment and decrement there, or I can just swap the wires around for the CLK and the DT. Now you might find actually the clock one wants to be the first input, so it's the one that is actually counting on the output A, so this blue one here. It should work the other way around. If I swap them around, it will work, but you might find so let's see, if I turn it clockwise now, yep, that's working nicely, and anti-clockwise working no problem as well. So actually, yeah, it doesn't really matter which way around it goes on this one. But like I say, sometimes if you get a few kind of missteps in the click, just swap the two inputs around, and you'll see if it's working correctly now. But that seems just fine here. As you can see, no problem. Now, remember, if you going back to the Opto switch, so the thing here in the book. Like I mentioned just before, if you wanted to sense direction, then you might want to have two slotted discs and just have one of the slots just a quarter of a phase out. So in other words, just 90 degrees shifted. So half of that slot is on when the other one's fully off. You see what I mean? We'll use the same principle. But yeah, this flowchart here, it's basically the principle of how to tell what direction it is when you've got two things that are slightly outside of phase from each other like that. And that's pretty much it. Two digital inputs, two rotary digital inputs that are slightly more advanced than just switches and buttons. Let's look at a real world application of that rotary encoder. So here I've got a mock-up of a DAB radio. I mentioned it before. I've heavily modified the flowchart that we had earlier. This is it. So you can see the rising edge and then D1, whether it's on or off, incrementing or decrementing A. Now, what happens here is a load of questions. So we're looking at the value of A. If it's A is 1, then it's asking you if you want to select dance hits radio station. 2, smooth classics. World music, and we could go on and on and on. We could have up to 253 or something like that, assuming, well actually no, you could have the full range, because here, because I'm not using the full range, I've got to tell it what to do if it goes past 1, 2 or 3 or under that. So in other words, if it's more than 4, just set it back to 1 and then bring it round here, and then it will just say there. So it will cycle round in that case. And if on this side, if it's 0 or more than 200, because remember, if it goes less than 0, it just goes round the clock to 255. So this is these two conditions here. We've got or, check there. So we've got two conditions that either one can meet the outcome. And then again, we'll just put it back to here. So it will just cycle round. If it goes that way, it will go there. And if it goes that way, it goes there. So you've just got a constant cycle there. Now, when that decision is made, then we look at the push button on the rotary encoder. Now, it's a bit of a weird one because this is a push to break switch, or normally open. You might notice when testing it, if you press it, that you get a 0. So if we get a 0 when it's pressed, we'll come along here and play the radio station. So if A is 1, if we've made that decision, when we press the button when the value is 1, then the value will still be 1 up here, and we'll play dance hits. If the value is 2, we'll play smooth classics. Now we could have if A equals 3 and then go round, but because it's only going to be 1, 2 or 3, because we've eliminated these two options, we can just say anything else is going to be value 3, world music. Now to get out of it, what we're doing here is using the push switch, again normally open, normally closed, push to break. But the thing is, we also want to make sure you've let go of it, because if you're still pushing it down and you come down here, it might just send you back into the playing radio station. So you want to have, a few ways of dealing with this, and we'll cover this in the inputs video. Just a way of stopping yourself clicking it back into the original thing by just having a check here that you've released the button. So it's the opposite way around. So if do 2's on this time, i.e. it's open, the switch has been released, then we'll carry on like that. Okay, here's the circuit in real life, having uploaded it onto the Genie. As usual, we're just using a breadboard to share the plus volts and the ground with the LCD and the rotary encoder. You can see here I'm in the beginning state, the LCD, and then as soon as I move this, I start adding data values, so it compares. That's going to be 1, 2, 3, and then if it's 4, it goes back to 1. If it goes down below 1, like 0 or 255, it will go on to 3, as with the flowchart. And then when I push the button, it just goes into the other state, so it just says what it's playing. And then push it again to get out of it. And that's it.